guys, it's me Jarvis, and today's lesson is on measuring gas pressures.
So before we had gauge technology, fluid columns were used to measure pressure. In fact, fluid columns are still used quite widely today to measure gas pressure, and they really do contain some of the fundamental ideas of fluid mechanics. So let's have a look and see what the pressure is at the base of a column of fluid. So here we have a column of fluid. It could be gas or liquid. In any case, the pressure on the base is equal to the force, the weight force of that fluid divided by the area of the base. So that's going to be the volume of that cylinder there, multiplied by the density, multiplied by gravity. Here we have the height, here we have the diameter to make the base, and we need the density of the fluid in there. That's given by the symbol rho. So the volume will be the area of the base times the height times the density times gravity for the weight force, where the density is rho. Divide the area of the base, top and bottom, we get this beautiful expression that the pressure at the base should be equal to rho GH, where the pressure is in pascals, rho is the density in kilogram per cubic meter, G is the gravity here, 9.81 Newton per kilogram, and H is the height of that column of liquid. Notice the area of the base doesn't matter. So this is the pressure exerted by a column of fluid at its base. So there are some more interesting facts about fluid mechanics. In fact, there are many of them, but certainly a couple of them from that world that we should pay attention to. And here's the first one. The idea that the pressure is the same at all directions, or the pressure is the same in all directions, I should say, at a point in a fluid. So at a point in a fluid, the pressure left, right, top, bottom, front, back are all equal. Okay, second interesting point about fluid mechanics here is that 2 points in a stationary fluid at the same elevation have equal pressures. So this comes from Bernoulli's principle and will be very useful to us as we explore the measurement of gas pressure here. So now we'll put it all together and measure the pressure of gases. That's actually what we wanted to do, so a little bit of fluid mechanics will help us with that. Let's look at the setup here. So here we have a cylinder of gas whose pressure we want to measure. It has a closed valve there. And we'll just use a long U-shaped tube here with some liquid, probably water in there for now, or some other liquid. And of course, because everything is open there on the atmosphere and the backside there, the valve is closed, the water in there is level. So when we open that valve, the gas pressure will be exerted on the left and push down the liquid on the left and push it up on the right-hand side. If the pressure of the gas is greater than the atmospheric pressure, this will be the situation. Okay, so then use that second idea that the elevation here being the same, the pressure is the same on these 2 points. So there you have the atmospheric pressure above and this column of liquid. The pressure fluid here is rho GH. So at that point, you'll get the pressure there that you don't know is the atmospheric pressure plus this fluid pressure, or P atmospheric plus rho GH.
So here we have the differential manometer we were just discussing. We'll exert a high pressure on the left-hand side and see what happens to the column of water. So here we have a high pressure on this side and a low pressure on this side, which is the atmospheric pressure. The greater pressure here has forced this side of the water column down and the other side up. Measuring the difference here, you can either use the ruler that we have here or just use this one, which I happen to have conveniently in my hand. And that's 282 millimeters. So this 282 millimeter column of water here is exerting a pressure equal to this pressure over here, and we can calculate what that is.
So looking back, the situation you just saw, that height of water was 282 millimeters, higher on your right than on your left. So H was 282 millimeters, and the pressure of the gas in the closed side was the atmospheric pressure plus rho GH, which was that density times gravity times the height of the column. So there's the density, here's gravity, and here's the height of the column, 0.282 meters. And that value there wound up, by the way, as newtons per square meter. That's a Pascal. That's very good. That wound up as atmospheric pressure, which was 101,325 pascals, plus this 2766. That was the additional pressure. So that the pressure in there of the gas, the one I exerted by my lungs, was 104 kilopascals. Okay, so a barometer is a variation on the same theme, and this one here uses what looks like an eudiometer, or a gas collection tube. And here you have the closed end of a cylinder on the top, and of course it's used to measure atmospheric pressure. We all know that. Atmospheric pressure acts down there on the bottom of that liquid. There's a vacuum in the top there, and the pressure of the fluid at the base of that column is equal to P atmospheric. The idea being there that the pressure of the fluid is the atmospheric pressure, and there's the zero vacuum above plus rho GH. That would give you the pressure of the atmosphere. Remember that 1 atmosphere, if you were to do this calculation, winds up being about 10.13 meters of water. It's a bit tall, so you need a denser liquid, and we use mercury for this one. If we do use mercury, it winds up that that column of mercury is just 760 millimeters in height. So that 760 millimeters of mercury exerts 1 atmospheric pressure, or 101.325 kilopascal. Here are some more pressure conversions: pascals, millibars, psi, bars, atmospheres, and torrs. Okay, so all these here are equivalent to 1 atmosphere. Anyway, torr is a millimeter of mercury, and there are 100 bars in an atmosphere, 14.7 pounds per square inch. So thanks everyone, have lots of fun with gas pressure measurement, and see you soon. Don't forget to watch the next 2 videos in this playlist, and stay tuned for our next lesson, lesson 24, real or non-ideal gases.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe.